Hello my friends and welcome back to the You Can Do TV channel. Scrap steel, after being crushed by a metal crusher, is placed into a 20-ton induction furnace, where it is melted at a temperature of around 1750 degrees Celsius. Induction furnaces use electrical induction to heat and melt metal, offering a clean and energy-efficient alternative to other melting processes. Capacities for these furnaces range from less than 1 kilogram to up to 100 tons, and they are commonly used for melting various metals such as steel, copper, aluminum. A significant advantage of induction furnaces is their ability to provide precise temperature control. Unlike arc furnaces, induction furnaces produce no combustion-related pollutants, making them an environmentally friendly option. However, one limitation is their lack of refining capacity. The raw material must be clean and free of oxidation to ensure proper melting. After melting, the steel is cast into billets of 130 by 130 millimeters for further processing. Once the billets are formed, they undergo the hot rolling process. The billets are reheated in a furnace at approximately 1200 degrees Celsius. Hot rolling takes place above the recrystallization temperature of the metal, allowing it to maintain a flexible and equiaxed microstructure. This prevents the steel from becoming brittle or work hardened during the rolling process. As the steel passes through a series of rollers, its thickness is reduced, and it is elongated into the desired shape, whether rods or wire. This hot working process improves the overall strength and structural integrity of the steel. The steel chain manufacturing process involves several steps to ensure that the chains meet high standards of strength, durability, and reliability. One of the most common types of chains produced is the round link chain, which is widely used in industries like mining, construction, and lifting applications. The process can be broken down into key stages: forging, bending and welding, quality control, and assembly. The first step in manufacturing round link chains is the forging of individual components. Steel rods are typically cut into appropriate lengths, heated in a furnace until malleable, and then shaped using forging presses or hammers. This process creates the basic links or rings that will form the chain. Forging ensures that the metal's grain structure is aligned, resulting in a stronger and more resilient product. Once the links are forged, master links, which are often larger or have a unique shape, are formed through a bending process. The steel links are bent into their final circular or oval shape, ensuring uniformity in dimensions and structural integrity. Following bending, the ends of the master links are joined together by flash welding or electric resistance welding, where the steel is heated and fused to form a seamless joint. This welding process is crucial for ensuring that the chain maintains its load-bearing capacity without weak points. Quality control is an integral part of steel chain manufacturing. Each chain undergoes rigorous testing to check for structural integrity, dimensional accuracy, and overall strength. Non-destructive tests, such as ultrasonic inspections or X-rays, may be used to identify any internal defects in the metal or the welds. Additionally, tensile strength testing is performed to ensure the chain meets specified load requirements. This reliability check helps guarantee that the chains can handle the required stresses in real-world applications. The final step is the assembly of the chain. The individual links, including master links and other components like hooks or connectors, are assembled into the final product. The assembled chains are then coated with protective finishes, such as galvanization or painting, to prevent corrosion and extend their service life. Steel wire manufacturing begins with the selection of high-quality raw materials, usually low-carbon steel billets. The billets are heated in a furnace and passed through a series of rolling mills to reduce them into wire rods. These rods are then pickled in acid to remove scale and other surface impurities. Once cleaned, the wire rods undergo drawing, where they are pulled through progressively smaller dies to reach the desired diameter. During this process, lubricants are applied to reduce friction and prevent damage to the wire. In the final stages, the wires may be heat-treated or galvanized for additional strength and corrosion resistance. Quality checks such as tensile strength testing and coating inspections ensure the product meets industry standards. The wire rope manufacturing process begins with wire rod drawing, where high-carbon steel wire rods are drawn through a series of dies to reduce their diameter to the desired size. This process is key in determining the strength and flexibility of the final rope. After drawing, each wire undergoes strict testing and quality control, ensuring compliance with performance standards. Testing is conducted at multiple stages, before, during, and after production, to guarantee consistent quality. Next comes the mixed wire rope stranding, where individual wires are twisted into strands, and these strands are then twisted together to form the final wire rope. Depending on the application, wire ropes can be composed of various materials or configurations to provide the necessary strength, flexibility, or resistance to wear and corrosion. The final product is packaged according to the standard in wooden or steel wheel reels for safe transport and storage. This packaging ensures the wire rope remains protected from environmental factors that could degrade its quality during transit or storage. For facilities with an annual output of over 100,000 tons, efficiency, precision, and adherence to rigorous standards are crucial in maintaining production quality and meeting demand in industries such as construction, mining, and maritime. The manufacturing process of shackles begins with cutting steel bars into appropriate lengths, typically from high-strength alloy steel. These steel bars form the base material for the shackle body and pins. Next, the shackle eyes are shaped through forging. In this step, the cut steel bars are heated to a high temperature and placed in a forging die where a press shapes them into the required dimensions. This step is essential for ensuring the shackle's durability and strength, especially in load-bearing applications. After forging the eyes, the shackle body undergoes bending. Using specialized tools, the steel is bent into a U shape, forming the main body of the shackle. The precise bending process is crucial to maintain uniformity and strength. Once the body is shaped, the parts are subjected to cooling, either through air or controlled cooling methods, to restore the metal's hardness and prepare it for subsequent machining operations. In parallel, the shackle pin is forged from a separate steel piece, forming a strong cylindrical part that will eventually secure the shackle. Machining operations follow, which involve threading the shackle pin and drilling a hole for the cotter pin. The threading ensures that the pin can be securely screwed into the shackle body, while the drilled hole allows for a cotter pin to prevent the pin from loosening. After machining, the shackles undergo painting or a protective coating process to enhance corrosion resistance and prolong their service life. Finally, the shackle is assembled, with the pin inserted into the body, the cotter pin added, and the product inspected for quality before being shipped. Steel slings are indispensable tools in the lifting and rigging sector, where heavy loads require secure, reliable handling. Manufactured from high-strength steel wire rope or chain, steel slings offer superior load-bearing capabilities, durability, and flexibility, making them ideal for lifting operations in industries such as construction, shipping, and manufacturing. This section delves into the detailed process of fabricating steel slings, with specific numbers on their capacities and the critical roles they play in the lifting industry. The fabrication of steel slings primarily involves two types: wire rope slings and chain slings. Both types are engineered with precision to ensure safety and optimal performance during lifting operations. Wire rope slings are fabricated from multiple strands of steel wires wound in a helical pattern around a core. The number of strands and wires within a rope affects its strength, flexibility, and endurance. The steel used for wire rope slings is typically high-carbon steel or stainless steel, which provides tensile strength ranging from 1,770 megapascals to 2,160 megapascals. The diameters of wire ropes range from 6 mm to 76 mm, 1/4 inch to 3 inches. The load capacity of a wire rope sling depends on its diameter and configuration. For example, a single-leg wire rope sling with a 12 mm diameter can handle loads up to 3.6 tons, whereas a 32 mm wire rope can handle up to 35 tons in a vertical lift. There are several configurations, including single-leg, double-leg, and multi-leg slings, each designed to accommodate different lifting setups. I slings and endless slings are also common, offering versatility in lifting orientations. The fabrication process involves cutting the steel wire to the desired length, followed by splicing or swagging the ends to form secure attachment points like eyes or loops. Swagging is a process that compresses the rope with a fitting to create a permanent termination, while splicing is the method of weaving the wire back into itself for a strong connection. Steel slings play a critical role in various lifting operations across industries. Their versatility, strength, and durability make them the preferred choice in applications where secure lifting is vital. The primary function of steel slings is to safely bear the weight of heavy loads. For example, steel wire rope slings can lift loads as small as 1 ton up to several hundred tons, depending on the sling's diameter and configuration. Chain slings, known for their ruggedness, can handle loads of over 100 tons in certain applications. Steel slings are designed to operate with a safety factor typically between 5 to 1 and 8 to 1, meaning that a sling rated to lift 10 tons has been tested to endure 50 to 80 tons of force without failure. This ensures a significant margin of safety, reducing the risk of accidents or equipment failures in critical operations. Steel slings can be customized for various lifting scenarios, from vertical lifts to more complex arrangements like choker or basket hitches. A single-leg wire rope sling, for example, might be used to vertically lift loads, while a double-leg chain sling could secure a load in a horizontal position. The flexibility of wire ropes makes them particularly useful in applications where the load might shift or where the lifting angles are not uniform. Chain slings, on the other hand, excel in environments where there is a higher chance of abrasion or sharp edges that could damage wire ropes. Steel slings, particularly chain slings, are built for long-term use in harsh environments. Wire ropes are treated to resist corrosion and wear, while chain slings are heat-treated and often coated for additional durability. Properly maintained slings can last for years, making them cost-effective solutions in heavy lifting operations. Breaking strengths of round slings in combination with standard shackles. And investigation round slings are a common tool in lifting operations across industries, often used in combination with shackles to secure and manage heavy loads. Despite their widespread use, a key safety concern arises when these components are combined, specifically when standard shackles and round slings of the same rated load capacity are used together. These combinations can introduce significant risk if the bend radius of the sling around the shackle body is not properly accounted for. Recognizing the need to address this safety concern, the Spanset Group, along with other industry experts, initiated an extensive investigation into the breaking strengths of round sling shackle combinations. Industry background: the Spanset Group has been involved in lifting, working at height, and load control for over 40 years, with a focus on safety and industry standards at both national and European levels. In response to concerns from key industrial clients and stakeholders, Spanset, along with partners Baja One Coca-Gay, Axiom GKS, Stalin Machine, and Baogay, conducted tests on the breaking strengths of round slings used with standard shackles. These tests aimed to eliminate the uncertainties surrounding the safety of such combinations by developing a more scientific approach to determining their breaking strengths. To address the uncertainties and improve safety practices, Spanset worked in conjunction with the Occupational Health and Safety Agency Metal Nordsut. The tests were conducted on 250-ton and 600-ton test beds, utilizing Spanset's facilities and a lifting beam manufacturer, Axiom. The objective was to determine the breaking strengths of specific round sling and shackle combinations. 4 round sling shackle combinations were tested, with rated load capacities of less than 10 tons and more than 10 tons. For load capacities under 10 tons, the braking strength was defined as 5 times the rated load, while for capacities greater than 10 tons, the braking strength was set at 4 times the rated load. The force was applied gradually during the tests, ensuring that it remained consistent to prevent sudden fluctuations or complete failures of the sling. In addition to static load tests, variable load tests were conducted, where the same part of the sling was subjected to cyclic loading to simulate real-world use. The range of load capacities tested covered the most commonly available products, from 0.5 tons to 150 tons. Traditional polyester round slings were tested, alongside high-strength fiber slings like the Span-Set Magnum X series. Standard shackles from a high-quality European manufacturer were used for consistency, and the shackles were deburred to eliminate sharp edges that could damage the slings during use. One key finding was that the round slings experienced their highest stresses at the bearing area on the shackle. To ensure accurate testing, the opposite ends of the slings were passed over a pin with a larger radius than the shackle to prevent unnecessary additional stress. After each test, the slings were examined for damage, and a detailed test report was generated. Of particular interest was the performance of the new Span-Set Magnum X round slings, which are made from high-performance polyester fibers. These fibers exhibit different properties than conventional polyester, offering increased resistance to damage from bending and pressure. In the tests, the Magnum X slings demonstrated superior performance, showing no damage to the load-bearing core, even when loaded beyond their rated capacities. The results of the investigation demonstrated that traditional safety guidelines for round sling shackle combinations may no longer be adequate, especially as newer materials with improved performance characteristics become more common. The high-performance fibers used in slings like the Span-Set Magnum X series showed significantly less susceptibility to damage from pressure and bending than earlier generations of materials. This investigation highlights the importance of updating industry standards to reflect the latest advancements in materials and technology. The Span-Set Group's efforts, in collaboration with industry experts, have provided valuable insights into the safe use of round sling and shackle combinations. By understanding the specific braking strengths of these combinations, manufacturers and users can make more informed decisions, reducing the risk of accidents and improving overall safety in lifting operations. The Nargesa MC200 pipe bending machine is a robust, versatile tool designed for a wide range of metal bending applications. It is crafted from welded and mechanized steel sheet, making it more durable than models made from cast iron. This machine is highly suited for creating circular shapes in various profiles such as round pipes, square bars, U profiles, T profiles, and flat bars. It is frequently used in the production of components for greenhouses, tables, chairs, doors, windows, and balusters. One of the key characteristics that set the Nargesa MC200 apart is its two-traction roller system. The two lower rollers are motorized and knurled, which provides superior traction. This knurling ensures that the material being bent has enough grip, allowing for precise and smooth operations. The safe transmission is facilitated by treated and flat pinions, which contribute to the machine's smooth operation and durability over time. The axes of the machine are constructed from treated and rectified steel, further enhancing their strength and longevity. These axes have a diameter of 40 millimeters, making them well suited for handling substantial loads and ensuring stability during the bending process. The useful length of the axes is 74 millimeters, providing ample space for bending various profiles and materials. Another important feature is the center distance between the lower axes, which is 286 millimeters. This spacing provides enough room for larger profiles and ensures the machine can accommodate a wide range of bending applications. The MC200's maximum bending capacity for round pipes is 2.5 inches, or 63.5 millimeters, a testament to its robust design and capability to handle larger materials without compromising the quality of the bends. One of the most important features of the MC200 is its upper axis bending regulation. This allows for precise bending of large pipes and profiles without causing distortion. The operator can adjust the upper axis to regulate the degree of bending, making it possible to achieve highly accurate curves even with large diameter materials. The upper axis also has a millimeter scale, which assists in ensuring precision in each bending operation. The MC200 comes equipped with 9 standard rollers and washers, enabling it to bend a variety of profiles such as square pipes, rectangular pipes, round bars, solid square bars, U profiles, T profiles, and flat bars. These rollers are easily interchangeable, which adds to the versatility of the machine and allows users to switch between different materials and profiles with ease. Additionally, the machine is equipped with side corrector rollers. These rollers help guide the material being bent, ensuring the operation remains precise and preventing deviations. They are especially useful when creating spiral bends, as they keep the material aligned throughout the process. The MC200 is designed to work in both vertical and horizontal positions. This dual position capability allows operators to choose the most suitable working orientation based on the specific needs of the project. This flexibility ensures the machine can fit into various work environments and handle different kinds of operations. The machine is powered by a motor with a capacity of 1.1 kilowatts, 1.5 HP, providing sufficient power to handle demanding bending tasks.